So, happy 2023 to you all. Thank you all for joining the call today. We have two excellent calls to kick off the year. So the first speaker is Chloe Baumas, who's going to talk to us about, well, where is the active mesopelagic zone in terms of carbon attenuation? So Chloe, over to you.
Thank you. So hi everyone, I'm Chloe Baumas. I'm doing a PhD in Marseille in France with Christian Tamburini and Frédéric Lemoyne. And I will talk about our recently new paper on a method. And yeah. So we are all part of the JETZON community, and we aim to focus on the understanding of the twilight zone, also named mesopelagic zone. And why are we interested in this zone? This is because it's poorly understood from almost any perspective, because it contains possibly the world's largest and least exploited fish stocks, and because it recycles 80% of the organic matter that sinks out of the productive surface layer. And so this latter point is particularly important as it is related to biological carbon pump efficiency. So briefly, you have photosynthesis, which trapped CO2 in the surface of the ocean. And because of the decay and interaction between organisms, some particles will be created. And when dense and big enough to sink, those particles are exported with the carbon trapped inside. And only the particles which escape the intense biological activities in the mesopelagic zone will sink below and will be sequestrated. So following this logic, the observed attenuation of sinking carbon flux should be higher than the organism's carbon demand, which are living in the mesopelagic zone. And if we represent it as a bar plot, the input bar in green should be larger than the carbon demand bar. However, all the processes involved in the calculation of mesopelagic carbon budget are really difficult to quantify today. And as a result, we constantly, and in most of study, obtain a discrepancy between the carbon demand and the particle export. So those values depend, among others, on integration of variables between two depths. So those two depths are obviously the vertical boundaries of the mesopelagic zone, because it is between those boundaries that the major attenuation occurs. So the mesopelagic zone is commonly placed between 200 and 1,000 meter depths. And if we take example to illustrate where the attenuation curve is cut, taking those boundaries, we can observe that it does not target always the good attenuation part. So the 200 and 1,000 meter depths come from a classification edited in 1957 after several years of discussion and debate. And the authors indicate themselves that there was little argument and confusion about the zones away from the surface due to lack of information. They already suspected subdivision, but without information on where to place them, they agreed on this classification. And even if they based conclusion on numerous scientific studies, it is clear with what we saw on previous slides that the choice of this fixed depth is not adapted to target the attenuation of the POC fluxes, which in addition can vary spatially and temporally. So alternatively, studies aiming to understand mesopelagic carbon budget use the mixed layer depths determined from temperature or density, the surface photosynthetically active radiation called PAR, or the PPZ corresponding to 10% of the highest values of fluorimetry. So I plotted here the mesopelagic zone placed according to the different method. To do this, I use CTD data from cruises in North Atlantic in PAP site in 2009, 2015, West North Atlantic, Arctic, Mediterranean Sea, and South Pacific. And we see that it's very variable with high range each time. So who is right, which method to choose? And so we saw that fixed depths are not adapted to the ocean with a dynamic and heterogeneous activity. And the values for mixed layer depths, PAR or PPZ, are only depending on one parameters, whereas several parameters of varying importance can describe the water mass. The diversification of the methods led to difficult comparison between studies, and the lower boundary is still fixed at 1000 meter depth. So how to target the real attenuation zone? To overcome this, we propose a new method based on signal rupture detection adapted to CTD data. So briefly, if we take the example of a man running, the method will take the raw signal and will split it into different regimes. So for example, sprint, high speed, walk, or even stop. And the mathematical theory behind rupture detection of signal are really well reviewed in Truong et al. 2020. And it gave us inspiration to apply it to CTD data. So difference here is that we do not apply it to a single variable, like the running man, but to a multivariate signal composed of 5 variables: oxygen concentration, fluorimetry, temperature, density, and salinity. And those variables were selected as they are often used to study water mass or biological processes. And the other reason is they are routinely used on almost all crews. So here you can see 4 examples of our method results. The first one is at PAP site in North Atlantic, the second in the Arctic, this one in Mediterranean Sea, and the last one in South Pacific. So the gray area is the zone delimited by our method. By the way, we call the method Rubalis. And what you can see is that the gray area can vary in depth, but also in length. And you have only 4 examples here, but we tested the method on 13 contrasted stations. And what we observed, what we can see here already, is that the variables that drive the boundary estimation are not always the same. So the main variable which seems to drive the upper boundary estimation seems to be the oxygen and the fluorescence. For example, here the blue structure and the orange one. And in contrast, the lower boundary reflect more abrupt changes in the signal, such as here, or can be placed after inflection point here, such as here or after this one. So here you have a sensitivity analysis that we conduct to know which variables drive the upper and lower mesopelagic boundary estimation. This is in percentage of variation, in A for the upper boundary and in B for the lower boundary. Again, it's the same 13 station with North Atlantic at the PAP site, West North Atlantic, Arctic, Mediterranean Sea, and South Pacific. And as you can see, oxygen is the main, the orange one, but in the sum, if we look at the sum of total variation explanation, other variables are also important, such as temperature here, or density here for the West North Atlantic, or fluorescence here. So thus, by combining all 5 variables, we avoid the potential variations that can be generated between one method or another when methods are based on only one parameter. So this graph is just to show you where is located the boundaries from Rubalis in gray regarding the other methods with the same graph previously. And as you can see, it is not fixed. And for those 13 examples, the zone is not below 800 meter depth. So that's good. We have a way to get boundaries, including 5 variables routinely measured. However, we need to verify if it is relevant regarding the sinking POC fluxes. So is Rubalis better to target the attenuation part? This graph shows horizontally the upper boundary found with Rubalis, and vertically the key point of the POC fluxes. So in mathematics, the key point corresponds to the point where the curve tendency starts to change. So in this case, the start of the attenuation. And as you can see, the result is a 1-1 bar with a good statistic with 0.94 R square. And in parallel, we calculate that 90% of the attenuation of the curves occurs between both boundaries. Thus, Rubalis targets the attenuation part of the curve without being too large around, and we decided to call the defined zone the active mesopelagic zone, or AMZ. I represented here the resulting carbon budget of the 13th station using gravitational POC fluxes and prokaryotic activities integrated between Rubalis boundaries. And with a comparison with the other method. And on the first graph, you can see the Z-score of the discrepancy. So to remind, the discrepancy is the carbon demand minus the input of carbon. And the Z-score is how far from the mean you are. So in red, you are higher than the mean. That means a smaller discrepancy, and in blue, the opposite. So what you can see here is that using Rubalis here, you are almost always in red. And so this shows that, that this leads to a less unbalanced carbon budget, let's say. And the second graph is a map of carbon budget using Rubalis. So obviously, even if the discrepancy is lower, Rubalis does not resolve all the uncertainties we have around carbon budgets, such as carbon input from particle injection pumps, chemolithotrophy, or from a carbon demand point of view, the respiration measurement uncertainties, or the choices of some parameters, such as the prokaryotic growth efficiency, which is used to calculate the pink bar here. But it improves a bit the precision that we have on carbon budget. So as a take-home message, Rubalis offers the opportunity to determine precisely where is the attenuation part of the active mesopelagic of the mesopelagic zone, and we called it active mesopelagic zone. As we can use it directly on board on the first CTD, we can adapt the sampling strategy, and so we have an opportunity to define optimal sampling depths. Rubalis help to decrease the discrepancy and the uncertainties we have around, and allow a comparison between studies. So just to show you that it can be easily used by anyone, from a practical point of view, we build a GitHub with a really detailed README where everything is written step by step. And the link is in the paper. I wrote it here, but it's in the paper in the material and method section. And you can run Rubalis on from 1 to as much as you want CTD at the same time. You just need to copy paste command from our GitHub, from the installation step. And after all the commands are written, and you just need to copy paste it into Spider, for example, because it's in Python, or in your computer Python terminal. So it's just a figure on how Spider is built. So you have the terminal console here. You just need to copy paste what is written in the GitHub, and then you can have graphs and the result shown. So thank you. I hope that I convince you to at least try Rubalis, and thank you.
Excellent. Thank you very much, Chloe. So open the floor to anybody who has any questions. So if you have a question, please just raise your hand and I'll bring you in. So Chloe, can I just start? Can I ask? It's sort of a technical point, and I probably missed it. When you were doing the comparison to the knee point in the sort of the FPOC, so what was that? Was that a backscatter signal, or was that yeah, that's the one. So your knee point, is that using particulate data or flux data?
It's flux data on which I fitted the attenuation curve, like the Martin equation.
And the How was the flux data collected? Is that from sort of sediment traps at different depths,
Yeah.
or snow catchers, or?
Yeah, mainly from sediment traps, except for PAP Cruise 2015, it's coming from a marine snowcatcher.
Right.
And for peacetime, it's coming from, we had a deep value, but we estimate the upper value at 100 meter depth from a satellite VGPM algorithm.
Okay, thank you. I can see Ken Bisler has his hand up. Ken, would you like to ask a question?
Thanks. And Chloe, I certainly appreciate what you're saying and trying to do. I think there's been a lot of miscomparisons because people don't do rigorously what you're doing. So appreciate the talk. What I'm still trying to get my head around is, well, one was Adrian's question, because it's very difficult to get a knee point with, say, a trap or comparable methods. So that's a difficulty at the top, and it's a pretty sharp boundary. But for your 5 variables, I'm unclear what really is driving the deeper boundary variability when you look at things like temperature, salinity, oxygen. Is it really the oxygen profile, or what's setting that deeper boundary predominantly, I guess? Yeah, that was the plot I couldn't see.
So the detection rupture is completely independent from POC fluxes data. It's only using those 5 variables. So the code detects the rupture detection at the bottom from the structure of the profile of those data. So it can be from changes of different variables. It depends. So the mesopelagic lower boundary is here. So you can see here that it really depends. It's not always the same variables. I don't know if I answer.
So sometimes if I look at the lower one, the orange means it's dominated by oxygen, say at the 3rd or 4th location is driving that boundary, but others, green means potential temperature. Is that how I should interpret this?
Yeah, it's potential temperature.
And have you ever got low-level light data to see how light compares to your densities, both at the top and bottom? You know, you mentioned 0.1% at the top. Do you know if studies have looked at the bottom too? Because ultimately, light will determine when there's photosynthesis, right?
I don't get your question, I'm sorry.
Yeah, I just wonder if you had compared light levels to these 2 boundaries.
Oh, as it the lower
Here we go, okay.
boundary is deep, I guess there is no light.
Well, there are some photons, so that'd be interesting to do too, to see if there's some common lower boundary in the deep water. But anyway, thank you so much.
Thank you, Ken. So if anybody else has any questions, please raise your hand. Just following on from what Ken had, I guess this is more of a technical question, Chloe.
Mm-hmm.
Is the, I don't want to get into too many details of the actual method, but is it linear in the sense that you can have relatively small changes in the signal across all 5 variables will indicate a transition, or a large jump in one of them? Would both of those happen, or is there some sort of non-linear weighting or sort of non-linear effect? I'm just trying to understand, I guess, what Ken was saying in terms of what triggers the definition of the lower boundary. If in some cases it's not necessarily linked to something obvious in one, but it's the cumulative effect from 3 or 4.
So I would not say it's linear. But for example, the lower boundary, it's well the change in structure, except this one, for example, the change in structure are less marked than for the upper boundaries.
Right.
But the method is still is still working, and the method when you run the code provide an error estimation, and so for all our case, it was not so, the error was not so significant, but it was higher for the lower boundary than the for the upper,
Okay.
because you have less strong changes in the structure here.
Right. I see that I've got some other hands up. I think Nathan was first. Nathan, do you want to come in with the question, please?
Sure. Hi. Yeah, thanks for the great talk. I agree. This is a really important question. I have one question on the timescales. So my intuition is that the vertical profile of oxygen corresponds to longer timescales than the vertical profile of chlorophyll fluorescence, if we think of a region with a seasonal cycle. So, and maybe maybe salinity, even longer timescales. So by mixing these different measurements, can we know what timescale of flux profile that these metrics are kind of responding to? Do we expect the upper boundary to be the upper boundary sort of instantaneously, or the average upper boundary over the past few months or year? How do you think about timescales in terms of this threshold that is presumably changing with time?
What I observed, because I use only data from previous cruise, but what I observed is when you have a long cruise, if a weather event occur, then the profiles can be completely different, and then you can't use all. I mean, it's not really relevant to mix all the CTD profile at the same time, and so you need to run rebalaise few times for one cruise, and so I think as we want to assess the carbon budget, I mean, we don't want this, but the carbon budget as it is from one measurement profile, so one snapshot of what is happening in the mesopelagic zone. And so you have one CTD profile corresponding with one oxygen concentration corresponding. So I guess it's like a snapshot. But of course, it will be really, really interesting to see the dynamic of the IMZ depth over season, over location, over little timescales, just to see how it's moving.
Yeah, thanks. I guess to sort of follow up in panel D that you're showing right now, the top of the mesopelagic zone that you identified is quite far below any of the chlorophyll. And it seems clear that the oxygen profile, which may correspond to a mixing event that happened further in the past, seems to be dominating this. So if I were to guess what the flux profile looks like in the moment that you took the profile, I would guess it was closer to, you know, the 10% chlorophyll level. I guess that's part of where the question was coming from.
I don't have pictures here to show you the different POC curves, but what I can say, because we did the calculation, is that the attenuation starts at the top of the gray area. But obviously, it's moving by the warmth between each station.
Did you also test the 10% chlorophyll metric, for example, regress that against your knee point to see if it was any better or worse? A predictor? Whichever other metrics, like 1% light or that 10% of maximum chlorophyll, the alternative metrics that you presented at the beginning.
Yeah.
You showed a regression of the rupture depth versus the knee point depth. Did you also regress the knee point depth versus other alternative metrics?
We tried something like that, but I think it was we tried to fit to see any correlation with the upper boundary or even lower, but in this case it's more the upper with other variables, but it was not corresponding exactly, at least. It was not correlated.
Okay.
And we wanted metric, we wanted variables that will allow to set the upper boundary, but in the same time the lower. So all the light-based method or chlorophyll are not really relevant for the deepest part.
Okay.
So
Thanks.
I think I'm going to have to sort of call a halt to question that. So apologies to John and Laurent, I know who got your hands up. So can I please just encourage anybody who hasn't had a chance to ask Chloe a question, please do contact her by email, or indeed, if you want to put the question into the chat during the rest of the call, then Chloe can hopefully respond to you. But thank you once again, Chloe, an excellent talk. And I say it really is an important topic, trying to disentangle how we define the mesopelagic. So it's great to